Greetings, scholars. Today we're going to take a look at Chapter 2, Section 5, Rational Functions. Learning targets. I am learning to analyze and graph rational functions. I am learning to solve rational functions. A rational function is the quotient of two polynomial functions, where a of x is a polynomial function, and so is b of x. So it's two polynomial functions, one on top of another. Now, b of x cannot equal 0, once again, because if it did, we would have an undefined function. So the domain of this rational function is the set of all real numbers, excluding those values in which b of x equals zeros, or the zeros of b of x. They mean the same thing. So we're going to use the limits, our knowledge of discontinuity, and end behavior to determine the vertical and horizontal asymptotes, if any, of a rational function. So here we have the concept of a vertical asymptote. Now, if you were using limits, we would make a table of values approaching negative infinity and values approaching positive infinity. And then we would narrow it down until we found which they were converging to. That's the long way to do it. We will do one example of that. Same with the horizontal asymptotes. We can also use this doing synthetic division. So we'll do one example using limits, and then we'll do one example using vertical asymptotes. Or not vertical asymptotes, synthetic division. So for this first one, we're going to find the domain of each function and the equations of the vertical and horizontal asymptotes. So the domain is probably the easiest because we know it is all the x values that work. So here we'll have x such that x cannot equal 3. And that is because we know that we can't have that 0 in the denominator. That also becomes our vertical asymptote, because it is the x value that can never ever happen. So x equals 3. Now for your horizontal asymptotes, we're going to do the limit approach. So let's go ahead. We'll have a table. We have x, we have y. And let's see. Let's just choose some pretty far out numbers. What if we chose negative 10,000 for this one? Let's do negative 1,000. Let's do negative 100, 0, 100. So I chose these randomly high numbers in equal intervals so we could see if our numbers were converging towards a certain value. All right. Now, if I pulled out my calculator, I would see that if I put in negative 10,000, I would get 0.993. If I put in, or sorry, not 993, 9993. For negative 1,000, I'd get 0.993. Negative 100, 0.9322. Then we had negative 1.33, 1.0722, 1.0072, 1.0007. So, excluding this middle one, all of these are close to which whole number? If you said 1, you would be absolutely correct. So the limit of f of x as x approaches positive infinity as we're going in the positive direction, it is getting closer to 1. The limit of f of x as x approaches negative infinity, as we're going forever in the negative direction, it is once again also getting close to 1. So here we have a horizontal asymptote at y equals positive 1. So now this way really isn't that sustainable, and it's a lot of guessing and checking. We don't like doing that in math because it takes too long and there's a lot of room for error. Let's go over here. Domain. For which values can x not equal? Well, because x is being squared, that means no matter what number I put in there, it'll always be positive. So we're going to have x such that x contains all real numbers. So there are no domain restrictions, which means there is no vertical asymptote. So now let's go ahead and find our horizontal asymptote. We could guess and check, or we could use not synthetic division, we could use long division. My apologies, long division. So I'll take the 4x squared plus 1, and I'll have the 8x squared plus 5. All right, so what times 4 will get us 8? Oops, don't forget, I forgot our placeholder, 0x plus 5. Answer is 2. So 2 times 4x squared gets us 8x squared. We don't have a 0 term, but then 4 times 2 is 1. Now we switch all of our signs and we get 3 right here. So our answer for our long division becomes 2 plus 3 over 4x squared plus 1. Now we know that this right here is the remainder, which makes this right here our horizontal asymptote. And here in a minute, I'm going to show you an even easier way to figure this out. So I'm going to go ahead and say horizontal asymptote at y equals 2. So, Mrs. Younger, is there a shortcut? Absolutely. So if we're given the function where we have our polynomial function ax and then a polynomial function bx, we really only need to look at a few key things. We want to look at our exponents. All right, so our exponents. Well, we know, first of all, vertical asymptotes. That's easy. We've been doing that since Algebra 1. Those are our real zeros occurring in our denominator. Horizontal asymptotes actually have its own set of rules. We look at the degree of our numerator and the degree of our denominator. Now, n, what you just have to remember here is n is numerator. So if the degree of your numerator is less than the degree of your denominator, you have a horizontal asymptote at y equals 0. If the degree of your numerator is equal to the degree of your denominator, you just divide the leading coefficients. And if the degree of your numerator is greater than the degree of your denominator, then there is no horizontal asymptote. So if we were to go back to this previous example that we did up at top, Here is my n, here's my m. Because n equaled m, I look at 8 divided by 4, and that gave me 2, which is that horizontal asymptote. So way easier. So now, let's go ahead and do a few examples from beginning to end. So we need to graph a rational function, simplify f if possible, and then follow the steps. 1, find the domain. 2, find and sketch the asymptotes, if any. 3, find and plot the x-intercepts and y-intercepts, if any. 4, find and plot at least one point in the test intervals to determine by any x-intercepts and vertical asymptotes. All right, so 1, find the domain. X such that x cannot equal -3 because we cannot have 0 in our denominator. So we now know we have a vertical asymptote at x equals -3. I'm going to go ahead and I'm going to come over here and I'm going to sketch that. So we have vertical asymptote at x equals 3. Now we need to find our horizontal asymptote. All right, horizontal asymptote. Here, our numerator degree is 0. Our m is 1. So n is less than m, which means we have a horizontal asymptote at y equals 0. So I'm going to go over here and I'm going to plot that y equals 0. Three, it said plot x and y intercepts. X-intercept says y equals 0. So 0 equals 6 over x plus 3. Right, and so 0 equals 6. So there is no x-intercept. How did I get that, you ask? I multiplied both sides by x plus 3. And we know that this becomes 0 and that crosses out. All right, next, we want our y-intercept. It says let x equal 0. So I have y equals 6 over 0 plus 3, so y equals 2. So now I have a y-intercept at 2. So I'm going to go ahead and plot that right there. Now we have to do our test intervals. And we break our test intervals up by our vertical asymptote. So the best way to do it is we have our interval. We have our x, and we have our y. We're going to split this up into 2. Because our asymptote creates 2 sections, a left section and a right section. All right, so this interval right here is going to be from -infinity to this 3. So I'm going to put -infinity to -3. So I want values that lie between -infinity and -3. I'm going to keep it simple. I'm going to go -4, -5, -6. And then on this side, I want the values from -3 to positive infinity. So I'll put -3 to positive infinity. And I'm once again going to make that super simple. I'm going to -2, -1, 0. All right, now if I were to substitute that into my function with a calculator, if I substitute -4 in, I get -6. If I substitute -5 in, I get -3. If I substitute -6 in, I get -2. All right, same. If I do -6, or -2, I get +6. If I get -1, I get +3, and then I get 0, 2. So what we just here is we just added 6 points that we can plot onto our graph. So here we're going to go -4, -6 is way down here. And then I have -5, -3. And then we have -6, -2. Now I'm going to make my smooth curve to plot that. Now I'm going to do the other side. -2, +6, way up here. -1, +3. We had that y-intercept right here at 0, 2. And we're going to do our nice smooth curve again. And there we have it. We have found the domain. We have found and sketched the asymptotes. We have plotted the x and y intercepts. And we have plotted points on the test intervals. So it is a long process, and we have quite a few more to do with these. All right, we have another example here. Once again, we're going to start with our domain. Remember, domain is what x cannot equal, so x cannot equal 3, because that would give us an undefined function, which means we have a vertical asymptote at x equals 3. So I'm going to go ahead and I'm going to plot that. At x equals 3. All right, now we have to look for horizontal asymptotes. The degree of my numerator equals 2. The degree of my denominator equals 1. So here we have n is greater than m. So if we go back and look at our notes, when n is greater than m, that means there is no horizontal asymptote. All right, so now we have to do our intercepts. X-intercept says y equals 0. So 0 equals x squared minus 7x plus 10 over x minus 3. Our goal is to isolate x, so I'm going to multiply both sides by the denominator. When that happens, we get rid of that denominator, and I still have 0 on my left side. And now we have a quadratic that we can solve pretty simply. And we get 0 equals x minus 2 times x minus 5. So x equals 2 and x equals 5. So there we have two x-intercepts. So I'm going to go ahead and I'm going to put an intercept at 2 and an intercept at 5. Now we have to go ahead and do our y-intercept. It says let x equal 0. So y equals 10 over negative 3. So negative 3 and 1/3 approximately. So I'm going to go up here. Here's 3. We'll say 3 and 1/3 is right around here. All right, so now we have our y-intercept plotted. Let's go ahead and do our intervals now. So interval, we're going to have 2 again from our negative infinity side to our asymptote and from our asymptote to our positive infinity side. So we'll go negative infinity to 3. And then we'll do 3 to positive infinity. And please ignore my cat if you can hear her. Then we have our x's and we have our y's. Let's go ahead and do 2 x's, 2 y's. So negative 2 is a pretty good one. And let's do negative 4. That way it gets a little bit more on that left-hand side. All right. And then 3 to positive infinity, 6 and 8. Now, Miss Younger just realized she made a mistake. Do you see this right here? This is negative 3 and 1/3. I plotted positive 3 and 1/3. So let's go fix that. We're looking right around here. All right, so if I substitute negative 2 into my function, I am going to get negative 28/5, which is approximately negative 5.6. So negative 2 comes in negative 5.6, so pretty close to over here. Negative 4 gives me negative 54/7, which is negative 7.7. So right around really close to 8. So what we have here is this curve that comes really up here and then super steep as it gets close to that asymptote. And Lord knows Mrs. Younger does not make the straightest lines on her tablet. All right, so now if we put in 6 and simplify that, we'll get approximately 4/3, which is 1.3. So 6 becomes 1.3. So here's 1. We'll say 1.3 is right here. And then 8 becomes 3.6. So 8, close to that. So once again, we're going to have a curve with a steep drop towards that asymptote. And we're just going to pretend it's the most beautifully smooth lines we've ever seen in our entire lives. All right, let's go on to another example. With this section, it's just going to be example after example after example, so you guys get a feel of what we're seeing. All right, so step 1, domain. X such that X is what? Cannot equal plus or minus 3. And that is because if I put in a positive 3, it'll yield 0. If I also put in negative 3, because it's being squared, it'll yield 0. Other than that, we have all real numbers. So here, we're going to have 2 vertical asymptotes. At x equals positive 3 and x equals negative 3. So here's our negative 3. So I'm going to go ahead and put in a vertical asymptote here. Then at positive 3. Now we have to look for our horizontal asymptotes. Now my n, the degree of my numerator is 2. M, the degree of my denominator is 2. Since n equals m, it says we need to divide our leading coefficients. And in this case, 3 over 1, which is 3. So we have a horizontal at y equals 3. So now, just based on this alone, and we haven't gotten to this, we're going to have 3 intervals to test. Negative infinity to negative 3, 3 to 3, and 3 to positive infinity. So keep that in mind. Step 3 asks us to look for our intercepts. So the x-intercept says y equals 0. So 0 equals 3x squared minus 3 over x squared minus 9. So if we multiply both sides by x squared minus 9, we get 0 equals 3x squared minus 3. 3 equals 3x squared. 1 equals x squared. Then plus or minus 1 equals x. So we have 2 x-intercepts at positive 1 and negative 1. Y-intercept says let x equal 0. So y equals negative 3 over negative 9, which is 1/3. So really, not that much higher. If here's 1, 1/3 would be right about here. Now automatically, we can already kind of see the shape that the middle interval is going to be taking. So we have 3 intervals to test this time. We have the interval from negative infinity to negative 3. We have the interval from negative 3 to 3. Then we have this last interval from 3 to infinity. So that's 3 sets of intervals. So because we have so much going on, it would be in our best interest to go ahead and put 3 test points for each interval. So let's do negative 4, negative 5, negative 6. We'll do negative 2, 0, 2, and that's because we already have our intercepts at 1 and negative 1. And then we'll do 4, 5, 6. Now, I trust that all of you know how to solve and substitute and solve. So I'm just going to go ahead and we're going to say that this is 6.4, 4.5, 3.9, negative 1.8, 0.33 because it's 1/3, negative 1.8. We'll do 6.4, 4.5, 3.9. Let's go ahead and plot those points. So negative 4, positive 6.4. Negative 5, positive 4.5, so right about there. Negative 6 is 3.9, so right about there. So here we go. First section. Boom. Boom. Negative 2 gave us negative 1.8, so close to that negative 2. And 0 gives us that 0.3, which we knew about. So we have that next section. And then we'll have our last section. 4 gave us 6.4. 5 gave us 4.5. And 6 gave us 3.9. So very similar, almost exactly to what we have on the other side. So that one had the 3 intervals. So once again, a lot of work. All right, so now we're actually going to talk about something special. We've talked about vertical asymptotes. We've talked about horizontal asymptotes. Now we have something we call a slant, or another term could be oblique asymptote. So it's that diagonal asymptote. So when the degree of the numerator is exactly 1 more than the degree of the denominator, so exactly just 1 more, then the function of the oblique asymptote is that quotient when we use our polynomial log division. So let's go ahead and use that information to do this next part. We're still going to do all 4 items. We're first still going to find our domain. Now, we have a quadratic function, so we need to go ahead and factor this. So x squared plus x minus 12, that's x plus 4, x minus 3. So x cannot equal negative 4, x cannot equal positive 3. So we have a domain of x such that x cannot equal negative 4 and positive 3. So that's 2 vertical asymptotes. At x equals negative 4 and x equals positive 3. So let's go ahead and plot those. So negative 4 would be right here. And positive 3 would be right in the middle of these 2 right here. All right, so now we have to find our horizontal asymptotes. So n equals 3 and m equals 2. So because n is greater than 2, we don't have any horizontal, but because n equals m plus 1, we have an oblique asymptote. So now we have to do that polynomial long division. So we take our x squared plus x minus 12. We're going to see how much it goes into 2x cubed plus 0x squared plus 0x plus 0. So we know this becomes 2x right here. And so we get 2x cubed plus 2x squared minus 24x. Switch our signs. Subtract, subtract, add. So now we have negative 2x squared plus 24x plus 0. All right, so now we're going to subtract 2 right here. And that'll get us negative 2x squared minus 2x plus 24. Switch our signs. Boom, boom, bop. Scroll down a little bit. We now get 26x minus 24, and this becomes that remainder. However, our quotient is 2x minus 2 plus our remainder 26x minus 24 over x squared plus x minus 12. So this right here is our oblique asymptote, which follows slope-intercept form. So I'm going to go to negative 2 on my y, 2, 4, 6, 8, no, it's right here, right in the middle. And then I'm going to go up 2 over 1, so up 2 over 1, up 2 over 1. And so what we kind of have going on right here, it looks like another asymptote at similar to that right there. So once again, we're going to have 3 interval sections based on my vertical asymptotes. Let's see if we can find any intercepts. X-intercept says y equals 0. So if I put 0 equals 2x cubed over x squared plus x minus 12. We end up getting 0 equals 2x cubed, so 0 equals x. So I have an x-intercept at 0, and then let's go over here and do our y-intercepts. It says x equals 0, and then I get a y-intercept of 0. All right, so we have a y-intercept at 0, which is right there. And then I have an x-intercept also at 0, so 0, 0. Worked out pretty nicely, didn't it? All right, now we have to do our intervals. We have 3 intervals. So this first interval we'll do from our negative infinity to our first asymptote at negative 4. Then we have our x and our y. So let's do 3 x's, negative 5, negative 6, negative 8. All right, then we're going to have an interval from negative 4 to positive 3. So let's do negative 3, negative 2, positive 2. Then we have one more interval. And this one is from 3 to infinity. So let's do 4, 8, and 10. 4, 8, 10. Now you can pick any numbers in this interval. I'm just trying to pick things that are going to be easiest. So I know you all know how to substitute, so we're going to go ahead and just put these in. I get negative 31.25 here, negative 24, then negative 23.27. All right. Then we get 9, which is super easy. 1.6, negative 2.7, and then the last one, remember this is x, this is y. We get 16, we get 17.06, and we get 21.27. All right, so let's go ahead and plot these. So -5 is right here. -31.25, so way up here. All right, then we have -6, which is right here, and then -24, which is right here. Oops, I'm going positive. What am I thinking? Let's start over. -5, -31.25, so right here. -6, -24, right here. -8, -23.27, so pretty close to over here. So we're going to have a smooth curve like this. All right, now we're going to do the middle part. We had -3, +9, so 4, 8, 12, so right around here. -2, 1.6, so really close over here. All right, now we have -2, +2, -2.7, so here's 2, 2.7 is like right around here. And so this one looks like that. Because we have the 3 sections, that middle section will cross the vertical asymptote. It's the end sections that will not. All right, we have 4, 16, 8, 17.6, so just a little bit higher. And then 10 is 21.27. So look at something like that. It is a lot of work. I'm not going to negate that. It is a lot of work. All right, going on. When the numerator and the denominator of a rational function have common factors, the graph of the function has removable discontinuity called holes at the zeros of the common factors. So now we have to determine any vertical asymptotes, horizontal asymptotes, holes, and intercepts, then graph the function and say its domain. So first things first, can we factor either the numerator or the denominator? The answer is abso-stinkin-lutely. So we get x plus 2 on the top, x minus 2 because that is the difference of squares. And then on the bottom, we get x minus 4, x plus 2. Now, notice we have 2 factors that can be eliminated because they are common. So when that happens, we have just the function x minus 2 over x minus 4. So this tells us we cannot have anything at -2 and +4 because of the vertical asymptotes. So I'll go down here real quick. 2 vertical asymptote at x equals 4 and x equals -2. All right. Let's check. And so our domain is x such that x cannot equal +2 and 4. We have to check for our horizontal asymptote. So our numerator is 2. Our denominator is 2 because n equals m. We divide a sub n over a sub m, so in this case 1 over 1. So we have a horizontal asymptote at y equals 1. So let's go ahead and put those in real quick. So we had negative 2. And positive 4. However, our negative 2 was the one that canceled. So that means my whole occurs at negative 2. Because that was the common factor. So that means that we have the whole. So whenever I put in negative 2 for x, that is where my whole will be. So my whole in this case is going to be 2/3. So over here, I'm going to put a whole at negative 2/3. All right. Vertical asymptote. That is our whole. So at just 4. We have a horizontal asymptote at 1. All right, so now we have to find our intercepts. So x-intercept says y equals 0. So 0 equals x minus 2 over x minus 4. 0 equals x minus 2. 2 equals x. So we have an x-intercept at 2. And then we have a y-intercept at x equals 0. So we get 1/2. So I have a y-intercept at 1/2. So I already know what shape this left side is going to be. So I can go ahead and skip that interval because I can already see what that shape is going to be based on the 3 points we've already plotted. So let's just do the interval from 4 to infinity. So from 4 to infinity. For x's, let's choose 5, 6, 7. Make it easy. 5, 6, 7. Which means our y's would be 3, 2, and 1.67. So we get 5, 3, 6, 2, 7, 1.67. So once again, we have that overall shape. We've done a ton of examples so far, but we are not done yet. Rational equations can also be solved by multiplying each term in the equation by the least common denominator of all terms in the equation. Hey, sugar, what's the least common denominator? Well, that means we have to find the common denominator first. So here we have x over 1, and over here we have x minus 8. We need these denominators to be the same. So we end up multiplying both sides by x minus 8 for x minus 8, and this one 1 over 1. So essentially what I did was I multiplied this first by our second denominator and this by our first denominator. So now we have x times x minus 8 over x minus 8 plus 6 over x minus 8 equals 0. Let's go ahead and put that all on one fraction. So I have x squared minus 8x plus 6 all over x minus 8. equals 0. Now, let's go ahead and multiply both sides by x minus 8. When we do that, it gets rid of our denominator. So now I have x squared minus 8x plus 6 equals 0, which means now that I am to a trinomial, a quadratic trinomial, I have one of two options. I can attempt to factor it, which in this case, I'm going to tell you it does not factor, or we can use the quadratic formula, which is what we do. So we have a equals 1, b equals negative 8, and c equals 6. I'm going to go over here. I know my quadratic formula, which you guys used a lot yesterday, or well, on Wednesday. Negative b plus or minus b squared minus 4ac all over 2a. So x equals positive 8 because we're negative of their actual b, so negative 8 is 8, plus or minus negative 8 quantity squared minus 4 times 1 times 6 all over 2 times 1. So if I simplify that, I get x equals 8 plus or minus the square root of 40 over 2. If I keep simplifying, that's 8 plus or minus 2 square root of 10 over 2. Keep going. Get x equals 4 plus or minus the square root of 10. So we have solved that equation. It has two answers. Boom. All right, keep going. We're on the last example. I'm going to solve one more rational equation. Now, unfortunately, rational equations can produce extraneous solutions, aka extra solutions that do not work. So we always need to check our original question. So once again, we need to get a common denominator. First things first, I want you to factor this side. See what this breaks down to. Okay, when we factor, we get 4 over x minus 4, x minus 2 equals 3x over x minus 2 plus 2 over x minus 4. Our goal is to get this. So if I take a look at this, I will notice that to get the same denominator over here, I'm going to have to multiply by x minus 4 over x minus 4. And this one would be x minus 2 over x minus 2. Basic fraction rules of finding common denominators. All right, so now we have 4, oops, different color. We have 4 over x minus 4, x minus 2 equals 3x squared minus 12x plus 2x minus 4 over x minus 4, x minus 2. Now notice, because these are two fractions that have both the same denominator, that means I can essentially ignore that denominator and only look at what's happening in that numerator because those denominators are the same. So now I have 4 equals 3x squared minus 10x minus 4. Well, let's go ahead and make sure this is a 0. Get all of our terms on one side. Now we're going to factor once again. So 0 equals 3x plus 2, x minus 4, Three x plus 2 equals 0. X minus 4 equals 0. So here we have x equals negative 2/3. Here we get x equals 4. We need to check solutions, because our goal is not to have any extraneous solutions. So when we check, let's first check x equals negative 2/3. Long story short, yes, if we put in our calculator, it does work. We get 9/28 equals 9/28. X equals 4. Long story short, no, it is undefined. At x equals 4, so it is extraneous. And it is undefined because right here, look at, we have x minus 4. If I put in a 4 right there, that means that entire denominator equals 0. All right, those were our so very, very, very long notes on rational equations and functions. You got this. You got this. If you have questions, let me know. Have a great day. Bye.